Okay, so here's an example of an inductive proof. What we're going to do is we're going to take this statement here, and we have to use inductive to prove this statement. And there are two steps to an inductive proof. The first step is proving the base case. So in the base case here, we'll take the first element that we start off with, which is just 1 cubed, and we'll show that for n equals 1, this statement holds true. So our base case is n equals 1, then the sum of all the terms on this side is just 1 cubed, which equals 1, and then we just have to check that this holds for this side. So if we substitute for 1 in here, we're going to get 1 squared bracket 1 plus 1 squared, all divided by 4. And if you do some algebra on that, 1 squared is 1, 1 plus 1 is 2, 2 squared is 4, 4 over 4 is 1, so therefore the base case holds true. Now the next step is called the inductive step, and it's probably the more important of the two steps. But what we need to do is show that because this holds for the base case, we can then generalize this to apply to any case after that. So any case after the n equals 1 case can be shown to be this. Now, you could imagine doing every single one of these by hand, just like we did above. So n equals 2, n equals 3, n equals 4, but that has the problem of going to infinity and requiring an infinite amount of time, which is kind of a pain in the ass. So instead, what we can do, or we need to do rather, is show that this holds true for the case n equals n plus 1. And I'll explain a little bit by what I mean. So let's say we want the general, the next step of this one up here. We would write it out if we were going to do the whole terms like this: 1 cubed plus 2 cubed plus dot 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 plus n cubed as we have above plus bracket n plus 1 cubed. Okay. So it's just this plus an n plus 1 cubed term, just continuing the pattern. And what we need to do to show this inductive proof is show that this equals this up here when we substitute n for n plus 1. So if I write out explicitly what I mean, just substituting in for here, we're going to get n plus 1 squared bracket n plus 1 squared all over 4. And if we can now show that this equals this, that will be our inductive proof done. So let me simplify this down a little bit. One simple step, which makes it a lot easier later on: n plus 2 squared over 4. Okay? So this is what we're looking for. But we can't start from here. We have to start from this expression here. And with an inductive proof, what you do is you're free to use your base assumption. So our assumption is that this statement here is true and correct. And if it is, that means wherever we find this term here, we can replace it with this term here. So you'll notice that down here, all of these terms from 1 cubed all the way up to n cubed, that is exactly the same as this whole term up here, which means we can replace it with that. So taking this down here, I can rewrite this expression here, right, just this top line, as n squared bracket n plus 1 squared over 4 plus n plus 1 cubed, which is just from this term here. And now I want to massage this around so I can show that this is equal to that. And if I can show that is true, that will be my inductive proof done. And doing that is actually pretty trivial, because all we need to do is re-express this with a common denominator, so 4 over 4. If you notice in here, we've got an n plus 1 squared term, which is common to both this term here and this term here. So we can factorize, we can pull it out the front, and we're going to get n plus 1 squared bracket n squared from this term here plus 4 bracket n plus 1, so that's the remaining n plus 1 in here, all over 4. If I expand this bracket out, I'm going to get 4n plus 4, and if you look carefully, you'll notice that n squared plus 4n plus 4, this here, is just equivalent to n plus 2 squared. So rewriting that out, n plus 1 squared bracket n plus 2 squared all over 4, and that becomes exactly the same as what we started off with up the top here. So that shows our inductive proof is done.